Yes, thank you very much for the introduction and the invitation. So today I'm going to talk about the work we've been doing on multiscale dynamics in nanoporous materials. I mean, it's going to be less mechanics, more physics, I would say. So let me start with a very naive introduction. So why are we interested in nanoporous materials, especially when we confine fluids inside this kind of nanostructures? So typically, there are two important aspects. The first one is the very large surface area. So typically, if you smoke cigarette, if you take 1 cubic centimeter of ashes, if you could unfold all the porosity, you get a few square meters already. But look, if you move to nanoporous material, typically zeolites, which are nanoporous crystalline materials that you find in nature, or activated carbons, you can reach typically a few thousand square meters per gram, if you can unfold the porosity. So you understand that for a physicist, if you confine a fluid inside this kind of structure, I mean, it's a bit naive, but most fluid molecules only interact with the surface and not so much with the other fluid molecules. So that's the first important properties, surface effects. The second one is the nanoporosity itself, because, I mean, nanoporous solids, the definition is that at least one of the pore dimensions is at the nanometer scale. And again, for a physicist, this is very specific because the nanometer, you know, it's not just a small scale, if you like. You really reach a specific point because the nanometer is typically the range of intermolecular forces in liquids. So if you take water, for instance, beyond 1-2 nanometer, of course it depends on temperature, but a water molecule doesn't see its neighbor. So it's the same for you if you are in a crowd. You see typically a few neighbors, and then after like 2-3 neighbors, you don't know what is going on, right? So this is very specific, and because of these two effects, we have new thermodynamic and transport phenomena. So I will give an example today. So I'm not going into the detail because I'm going to illustrate this, but typically what is important is usually in mechanics we use continuum level approach like Navier-Stokes equation for hydrodynamics. Here, forget about this, because at this scale, I'm not going to explain this today, but in short, the typical time scale it takes to transfer the molecule from one side of the porosity to another, so typically 1 nanometer, the time scale is comparable to the time scale to relax stress in fluid. Okay? So usually in hydrodynamics, you assume that the momentum transfer takes a long time so that you can assume that the fluid particle is fully relaxed. Here it doesn't work. That's why there's a breakdown of continuum level approaches. Okay. So typically, because of this breakdown of continuum level approaches, we need to turn to a different physicist model. So we're going to use statistical mechanics because it's based on molecules, so it's the perfect frame. And this is where we run into problems. Because for self-diffusion, so self-diffusion is you're looking at one molecule and you're following its path, its trajectory. We have many models. So, I mean, we have Brownian motion, free volume theory, surface diffusion, etc. Okay? But that's easy. The problem is that usually in complex system or engineering approaches, what you care about is not really self-diffusion. It's permeability, so really the mass flow, mass transport of molecules. And so we will see this later, but so the key transport property is permeability that you do in engineering experiments. And for this permeability, there's only one microscopic theory, which was built by Pierre-Gilles Degennes a very long time ago. I think it was 1959 or 1969, I don't remember exactly. That's the only microscopic theory for permeability. And this is the goal of today's presentation, to show you whether it works or not at the microscopic scale. Okay, so usually, like I said, it starts with permeability. So permeability, it's based on Darcy equation. It's a very simple equation. So you have a porous material here. You apply a pressure gradient. And usually, if the pressure gradient is not too large, you see that there's a direct relationship between the flow of molecules and the pressure gradient, which is the driving force. Okay? And the parameter here, so rho is the density. You assume that the fluid is incompressible. And big K is known as the permeability or permeance. Okay? So that's the kind of whole picture. What is interesting is that you see this is simply a linear relation, which is exactly consistent with the Onsager theory of transport, which is a linear response theory. So Onsager came a century after Darcy, where this time you write, I mean, that's pure thermodynamics, that the flow of molecule is directly related to the corresponding driving force. And the corresponding driving force in thermodynamics, if you're looking at the number of molecules passing through the system, it's not the pressure, it's the chemical potential. In thermodynamics, pressure is related to volume and number of molecules is related to chemical potential, okay? But that's the thing, if you use Gibbs-Duhem equation at constant temperature, you can relate the pressure to the chemical potential. If you assume that the density is constant, so in compressible flow, you can relate these two parameters, and you see that's the beauty of it, that not so many people are aware of, that in fact the permeability is directly related to what we call the collective diffusivity, and the collective diffusivity is a microscopic quantity that you can measure with neutron scattering, for instance. So you do non-permeability experiments, just a static problem. If you can probe we'll show this in detail later, but if you can probe the velocity correlation in the fluid at rest, you get exactly, and this is not an approximation, it's an exact derivation, quite simple in fact. Okay, so let's go one step forward. So we have this Onsager equation, which as I just showed you, is kind of equivalent to Darcy equation. You add mass conservation, which relates the change in the local density to the divergence at the flux at the time t, and you end up with this differential equation, which is just the combination of these two equations. Now this is where I'm going to introduce the concept of de Gennes narrowing, which is in fact quite simple. What you do is you solve, I mean this is a nasty equation, I know that this community is very good at solving this kind of problem, but for me it's already too complicated. So what we do is we solve this equation in Fourier space, okay? So the Laplacian here introduces a q squared term, which is the wave vector. So it means that what we're doing now is not to looking at the macroscopic flow transport, but at the flow at a given scale defined by the wave vector. So q is 1 over the distance. It's 2 pi over the distance. So this equation is far simpler to solve. And here the term that you have, which is related to the chemical potential, it's the derivative of the free energy of the system with respect to the density, the Fourier components of the density. It's the Fourier component of this chemical potential. And this is where we introduce de Gennes narrowing. So the idea of de Gennes is the following. You write that the free energy of your system is simply the free energy corresponding to density fluctuation. So your system is at equilibrium, but you have, because of thermal motion, you have some density fluctuation over wave vectors q. And we simply write that this is a sum of independent modes. So you see, you only couple density fluctuation, so this is the conjugated density fluctuation, over a wave vector. And the weight here, S of q, is the static structure factor. So S of q is what you measure with X-ray diffraction. So that tells you, we see an example here for the bulk fluid, that tells you that you have, even for a fluid, there's no crystalline structure, but you see some correlation peak. And the wave vector q, where you see a bump here, is typically, 2 pi over this q vector gives you the typical distance, if you like, between fluid molecules. Okay? So this equation, in short, tells you that you see that when S of q is large, it means that it minimizes all fluctuations corresponding to this large value in S of q corresponds to a minimum in free energy. Okay? And every density fluctuation that brings the system far from the S of q distribution costs a lot of free energy. Okay? So if you combine this, you end up with this simple equation. So this is this diffusion function, which depends as a function t, tells you how fast a density fluctuation relaxes in the system. So again, the simple picture is the following. You have density fluctuation. They occur because of just thermal motion, and they will relax fast or slowly. Okay? And the way they relax fast, you see, you have this time constant is proportional to S of q. So it means that, if S of q is large, you are close to the thermodynamic equilibrium. So the time the system relaxes is slow, because it does not cost a lot of energy to bring the system. The system is happy from a thermodynamic point of view. But if S of q is small, it means that you are bringing the system very far from its free energy equilibrium. Okay? So the typical time it takes to relax, it's like a spring. Relaxes much faster. Okay, so this is the picture of de Gennes narrowing. Okay, so this is the simple system we looked at. So I mentioned this zeolite, so nanoporous crystalline material. The size of the cavity is typically a few angstrom, and we do a very simple fluid, a Lennard-Jones fluid, so a single sphere, which is supposed to model methane. First thing we looked at is the adsorption isotherm. So this is a molecular simulation. I'm not going into the details, but if you change the pressure here, fluid pressure or the chemical potential, because as I said, it's related, this is typically the number of molecules that you get. So this is a log scale. We get the typical, for those that are familiar, this typical shape, which is a Langmuir adsorption isotherm. So you have at low pressure a very fast increase in the adsorbed amount, and then you saturate as you reach the maximum capacity of the porosity. And the big colored points are simply the different fluid loadings that I'm going to consider in the rest of my presentation. So as you understand from de Gennes narrowing, the key quantity, in fact, is the structure factor, S of Q. And that's the beauty, again, that's related to what I said, that when I told you inside the microscopic physics, you have the macroscopic response in Darcy equation, you can see it here. So that means that, again, if you measure this structure factor, you get a lot of information already on the dynamics. So this is what we obtained. So it's the S of Q as a function of the wave vector. So this is for the different loadings that I mentioned. So low loading, high loading. And what you see that we found very interesting is you have two important features here. So first of all, you see these strong Bragg peaks. This is not a fluid feature. This is what you expect for a crystal. And this is typically the signature of the crystalline zeolite. I want to insist here. What I measure does not include the zeolite. It's only based on the fluid, okay? But it's because the fluid is confined inside the crystalline structure. The crystalline structure imposes, an underlying crystalline pattern. And this is what you see. I will come back to this. Now, the second interesting result is you see that there's a small bump here, which is located at the same position as for the bulk fluid. This is what I mentioned earlier. This is typically the distance between fluid molecules. So let's stay 1 minute on these Bragg peaks. So took us a lot of time to think, how do we deal with this? Because like I said, it's the own feature of the fluid, but it's only because it's confined in the periodic system. Okay, so it's not strongly related to the dynamics of the fluid itself. So what we did is to correct these Bragg peaks by instead of taking the complete part of the structure factor. So I recall you that rho of Q is the Q Fourier component of the structure. Instead of taking the static part, we took only the fluctuating part. So basically, you remove the static contribution. Why do we do this? It's because we know, again, because of this crystalline structure, that fluid molecules will always relax in a state that tend to reproduce this crystalline periodicity. Okay. But it only relaxes toward this. So what we do here is by taking the fluctuating part, we simply look at the dynamics, if you like. And when you do this, so it's a zoom, so you see that, of course, as expected, the correction only applies where you have the Bragg peaks. You see it here with the zoom. And what is interesting is, in fact, where you have a Bragg peak, your fluctuating part is a minimum. And this was completely not intuitive to us. So what it means with wavy hand arguments is that the fluid is so correlated because of the crystalline periodicity that the fluid contribution to the structure is actually less correlated. So basically molecules are forced to follow this pattern so that they interact less for this given the specific wave vector. Okay? Okay. So what we wanted to do, because you understand that what I'm trying to do in the rest of my presentation is to relate microscopic physics and the macroscopic measurement. So first, let's do the macroscopic measurement with molecular simulation. It's doable. So you do typically, you mimic with molecular dynamics, you mimic the flow, like in an experiment, the flow induced by a chemical potential gradient or pressure gradient, because we know how to convert one into another. And again, you remember this Onsager equation. So you measure, you change grad of mu, you check that you have a linear response between the flow rate, so the density times the flow rate is directly the flow. So you see that you have so this is again the different loading, low loading, high loading, but you see that for a given loading you have a beautiful linear relation as expected for small chemical potential gradient or pressure gradient, and the slope directly gives you D0. So we do have our own macroscopic measurement with molecular simulation. But again, this is not the key point. I mean, what I just showed you is very standard in the field. What is interesting is to look at the connection with the microscopic physics that I just described. So, like I said, so if you solve this equation in a Fourier space, so I showed you that the typical density fluctuation relaxes with this time scale. And if you write in parallel that your flow is a response not to the chemical potential but to a density gradient, you get the second transport coefficient, dt. So the question is, if you compare these two equations, you see that the transport coefficient to a density gradient should be directly related to the macroscopic permeability through this S of Q, which is again this de Gennes narrowing. So first you take the limit when Q goes to 0. So Q goes to 0 means infinite distances. So we are at the engineering scale, okay? Does it work? Yes, it works. You see that if you take exactly the structure factor at a vanishing wavelength, so infinite distances, you get a very nice correlation. So I'm not going into the details, but again, we looked at different fluid loadings, and also because the matrix is anisotropic, we compared in different directions, and this field symbol is because we also looked at a system where the matrix is frozen, because we had questions about like if the matrix is flexible, the solid matrix, or if the matrix is frozen, do you see differences? Well, the answer is we don't seem to see any differences. I don't know why we did this actually. I think it's Jean-Louis Barra, my colleague, who insisted on this. Okay, so let's continue. So again, that's the same equation that I just showed you. So it's the relation between the transport coefficient to a density gradient and to a chemical potential gradient. So we just found that this worked. But there's one thing that is really nice here, that in fact, if you compare these two equations, like I did with the RC equation, you see that there's a direct relationship between them with the density here and KBT, which is the thermal energy. So, I mean, believe me, but if you replace here d mu over d rho, you get this equation. So you see that there's what is known as the thermodynamic factor gamma, which is again something that is a pure thermodynamic coefficient. There's absolutely no dynamics into this. And what is nice here is that this is the change in density when you change the chemical potential. And you remember, this is what I showed you with the adsorption isotherm. It was as a function of pressure, but you can relate one into another. So that means that if you do adsorption experiments, no transport, you get directly the connection. And we checked here. So you see, we checked that if you replace this S0 by 1 over gamma, you see, you get a very nice correlation. So you do adsorption experiments, you do structure experiments, and you almost get the dynamics of your fluid, which is not completely true because you still need D0 here. I mean, there's a trick at some point. Okay, so let's move forward. So what I showed you here, just the limit at vanishing wavelength. Okay, so wave vectors. So infinite distances, but like I told you, I mean, the de Gennes narrowing is a theory that relates transport at every wave vector, in theory. So let's look at this. So like I said, you measure typically this, it's called intermediate coherent scattering function. It's a complicated name. It's what you measure with neutron scattering. Okay? So like I said, looks complicated, but it's very simple. You create a fluctuation in density with a given wave vector at the time t equals 0, and you look how fast it relaxes to 0. Okay? So what you get is that, so I'm not going too much into the detail, but as expected, you see that for small wave vectors, so large distances, fluctuations relaxes slowly. And what is at higher wave vector, because it's very short distances, relaxes very fast. Okay, so this is what you see here. You see that the typical time it takes to relax these density fluctuations vary by orders of magnitude. But this is expected. You see this for bulk fluid as well. Now, what is interesting is Now, if you plot here 1 over the typical time scale as a function of q, you see this pattern. So you see that here you have a minimum in this typical time, and the green arrow tells you, we will go into the details later, but just qualitatively. This green arrow tells you where the fluid correlation peak is in the structure factor for the confined fluid. So it means that you already see that de Gennes narrowing works qualitatively. That you do predict that the typical time scale it takes to react follows 1 over the structure factor. So that's exactly what I said before when I said if you are at a maximum in the S of Q, this is a low free energy cost, so the relaxation is very slow, and vice versa. Okay, but let's go into the details. So does it work? So again, you remember, in short, de Gennes narrowing can be summarized as this equation. So you have the typical transport coefficient, D0 is the macroscopic limit, and S of Q is the structure factor. So again, as I said in the previous slide, you see that de Gennes narrowing is observed around the correlation peak. Okay, you see that here. Sorry, I forgot, I need to say. So here what I plot is dTq time the structure factor, okay? So it's supposed to be constant and equal to D0. So what you expect here is to see a plateau. So as you see, you do see a plateau. It works quite well. Especially you see that around the correlation peak, you see, I mean, there are some fluctuation and some uncertainties, but overall it's quite flat. So that means that the features that are observed in the collective diffusivity are also observed in the S of Q and vice versa. And in particular, I don't have time to show this today, but if you look at the self-diffusivity, you don't get this behavior. So it means that, you know, because someone could argue, okay, but maybe it's not a collective effect, maybe just your particles independently. I mean, it's never independent because self-diffusivity is also affected by the other molecules, but it's called the tracer diffusion. So one could argue that the tracer diffusion is also affected by this. But no, because in the tracer diffusion, you will never see the fluctuations like I showed you here, okay? It's actually flat. So that means that if you correct the self-diffusivity for the structure factor, it's actually completely wrong, doesn't work. So it's really a collective effect. Now you see the big crosses here, we decided to leave this point, it's what you get if you don't correct the structure factor for the Bragg peak. So that's why we did this. We actually did it a posteriori, because first we tried with this. But it means that when I corrected the Bragg peak in the fluid structure, it's really needed. So you really need to look at the fluctuating part of the structure factor and not the total structure factor. It's essential, as I wrote here. So now, what is interesting? In black, it's the same data, but for the bulk fluid. So it's just scaled by a factor 10 because otherwise they overlap and it's not so nice. But it's in the log scale, so it's just shifting by +1 decade. So what is interesting is you see that de Gennes narrowing also works for the bulk fluid, but in fact, the range of Q values over which we observe de Gennes narrowing is smaller for the bulk fluid. So it works better for the confined fluid. So what we believe is the following, that in fact, because you have severe confinement in the nanoporosity, you are more governed, if you like, by these structural effects, okay? Because the fluid tends to be more correlated from a static point of view. So that's why we believe that it works better for the confined fluid. So at a large Q values, you see that for both fluids, I mean the bulk and the confined fluid, doesn't really work, but that's what's completely expected. Look, it's a microscopic theory, so there's a limit. The limit is typically, in fact, the problem is not the microscopic theory, it's Onsager theory. Because Onsager theory assumes that you are at a scale that is large enough so that you can assume local, what we call LTE, local thermodynamic equilibrium. Now, if I tell you that here you are at the scale of the one molecule, it's easy to imagine that, of course, you no longer have local thermodynamic equilibrium. So it's not a failure of de Gennes equation, it's actually more a failure of Onsager formalism. Now, at large Q, and this was I would say, the disappointment for us, at large Q, the problem is you see that we also observe departures, so it's not too bad actually for the confined fluid because it oscillates, but you see that you remain very close to 1, so it's actually a good estimate, but it doesn't work. And here, this is another breakdown, which is due to the fact that at large scale, you start having collective effects. So you remember I told you that this is my last slide, then I conclude. You remember when I introduced this equation, I told you the big assumption is here, that you assume that you have the free energy is a sum of independent modes. Okay? But in practice, and there's a well-known theory in microscopic physics that is called the mode coupling theory, which is well known in the field of the physics of glasses, where in fact you show that you have a coupling between these different quantities. So a Q vector does couple with a vector Q prime that is different, which is what we ignore. And the problem is that, I go back to the last slide, the problem is that here, of course, at large scales, you do have these effects that come into play, okay? And again, what is interesting is you see that it's, in fact, more pronounced for the bulk fluid, because in the bulk fluid, you really have, at some point, a scale-dependent hydrodynamics with these collective terms, with this coupling. And in fact, the coupling is not so pronounced in the confined fluid. And again, this is due to this extreme confinement where most, you remember what I said in my first slide, most fluid molecules, they interact with the solid, a bit with the other fluids, but because of the confinement, there's a sort of cutoff, so they don't really see neighbors very far from them. So just to conclude, I think I'm right on time, 25 minutes. So I showed you a simple physical model, which rely only on available parameters to simple experiments, and it seems that it's able to describe the permeability in nanoporous media. What was a surprise to us is that, I mean, now we understand why, but it was a surprise at first that the validity of the model is actually better for the nano-confined fluid than for the bulk fluid. And despite the simplicity of the system that we looked at, I mean, a Lennard-Jones fluid is after the hard sphere model, is probably the simplest model you can think of. But we actually expect that this prediction should also work for water or complex fluid. I mean, there's no reason in the derivation why it should fail for other fluids. And so what we like very much about this work is the fact that it allows predicting and rationalizing macroscopic transport in nanoporous media, but from a very simple microscopic picture. And with this, I thank you for your attention.